So it has been a while. Let's try to recall we have learned last time. We had learned a very important theorem, the midpoint theorem. Very important. As we mentioned before, there are different ways to formulate the theorem. The way we picked is we start with a triangle. A, B, C. We pick a midpoint. It's slightly different from what we learned last time, but it's equivalent. What we do is we draw parallel lines. This will be F and E. So what we assumed, G is the midpoint. Assumption. And the two lines, GE and GF, they're parallel lines. The conclusion is E and F, they are both midpoints. So we have the 2 points, we can connect them. I will use a different color. The conclusion is this new line turns out to be parallel to AB. Moreover, we have the sides of this triangle are half of this triangle. We have EF over AB equals EG over AC equals FG over BC is 1/2. A little bit long, but this is the midpoint theorem with minimal condition. We start with a midpoint. We can draw parallel lines. We have a lot of conclusions. This is a very important theorem, not only the conclusions, but also the argument we used to prove it are also important. Not only for this, they are also important if you want to generalize the midpoint theorem. Okay, a generalization. I will redraw a triangle. Oops. So instead of the midpoints, I can find the 1/3 and 2/3 points. I call them G1 and G2. Then we draw parallel lines. It's very similar to what we had before. Just we have two pairs of parallel lines. Let's label the point similar to what we have done before. I call this F1, F2. Then the same conclusion holds. Okay, the second step, the same, draw parallel lines. G1, F1 parallel to BC, G2, F2 parallel to BC, G1, G1, E2 parallel to AC, G2, E1 parallel to AC. It's what you see on the graph. The conclusion is similar. The previous one, E is a midpoint, F is midpoint. So here, F1, F2, 1/3, 2/3 points. E1, E2, 1/3, 2/3 points. Similar. Then we connect the new segments. Our next conclusion is and we have the called similar ratio. Okay, so there's many of them, so I skip it, but you should be able to figure them out. For example, G1F1 should be 1/3 of BC. E1G2, 1/3 of AC. E2F2, 1/3 of AB. It's similar what we had over there. Just replace this 1/2 by 1/3 and 2/3. This is much more complicated than the previous one, but it can be proved using the same argument. So for the previous one, the tools are congruent triangles. The tools and the parallelogram. For example, because we draw it in this way, these two lines are parallel, these two lines are parallel. So ECFG is a parallelogram. We use this property in our proof of the theorem. For this one, we use the same property. Congruent triangles, a lot of them. You check these two triangles are congruent. You check these two triangles are congruent. Same argument, but more steps. It is a similar argument that okay. So this is our first generalization of the midpoint theorem. Now you can see we can further generalize it from 1/2 to 1/3 and 2/3. So we can to 1/4, 3/4, 1/5, 2/5. We can go to all rational numbers, the same argument. So we have the rational generalization. In this week's homework, I will ask you to fill in the details of this generalization. You will see how to use congruent triangles and parallelograms. For example, these two lines are parallel to these two lines. So this is a parallelogram. Then use the properties of the parallelogram. So, so this will be the homework. That's the first generalization. More generalizations. Okay, so let's again recreate the triangles. Label A, B, C. Because we are considering the more general case, we will only focus on the most important properties. We have a lot of this, but we pick the most important one. What are the assumptions? The assumption is okay, The assumption is we pick 2 points on the 2 sides such that the 2 sides, these 2 sides, they have the same ratio. This is the only condition we have. Jessica, pay attention, Jessica. So the conditions here means the 2 sides, they have the same ratio. If this is 1/2, then we go back to the midpoint theorem. If this is 1/3, is our previous generalization. 2/3 also works. 1/4, our homework. So the same argument applies to any rational number. So this any rational number. The conclusion is very important. So you can see it's a generalization of the midpoint theorem. It's a big generalization. If this is 1/2, we have this 1/2. This is kind of the midpoint theorem. If it's 1/3, it's 1/3. This will be what you will prove in this week's homework. So the same argument, congruent triangles and parallelograms can be used to prove this theorem for any rational numbers. Okay, let me stop for a few seconds. Check with Aaron. Any question about the statement here? Just compare this with the midpoint theorem. If this is 1/2, this is 1/2, the midpoint theorem. It's a generalization, and it's a far-reaching generalization. Amy, what about you? Okay, so we haven't proven it yet. We will skip the proof because you can see they'll be much more complicated than the previous one, more steps, but it can be proved using the same idea. Okay, so we will take this for granted. What we proved a few special cases. If this is 1/2, this is 1/2. That's our midpoint theorem. We prove it. If this is 1/3, this is 1/3, this is the previous one. 2/3 also works. 2/3 also works. So we believe, okay, we tell ourselves the same argument works. Okay, so the same argument. Okay. Okay, George is back. Okay, so now we give the main theorem. We don't have to restrict ourselves to rational numbers. This works for any number. Okay. So final form. Rational or irrational. As long as they have the same ratio, then this line must be parallel. Moreover, the two sides have the same ratio as what we have in the condition. Okay, this is a very important theorem. Today we will use this theorem repeatedly. So let me box this. We will use this repeatedly. Oh, I missed this. Okay, let me check if you remember some of the theorems with assumptions we learned in the course algebra. How do we move from a statement of rational numbers to a statement about any numbers, irrational or rational? Okay, Lucas.
Is this like an online class for 11.9? No,
Uh, so it's a different class. So this is what we have learned last week. No, not last week, the week before break.
okay, got it.
Uh-huh. So you don't have to be here if you have learned mastered what have learned last time. Okay. So there's a fundamental assumption of algebra. And actually it's algebra or arithmetics. Let's try algebra. How do we move from conclusions of rational numbers to all numbers, rational or irrational? This is the fundamental assumption. We will assume instead of this form, we will use this one. Okay, so from now on, we will call this the big theorem. If the 2 points are given such that they have the same ratio, then they must be parallel, a big theorem. We didn't give the proof, we proved a few special cases, and we take the general case for granted. Okay, so we proved a few special cases. Okay, some of you learned similar triangles. You might say, oh, that just mean these two triangles are similar. Amy, do you have this question?
No.
Okay. So because this is theorem, is introduced before we learn the similar triangles. This is used to derive a lot of the theorems about similar triangles, which is to say this is the foundation for any result we can see about similar triangles. So without it, we cannot prove much for similar triangles. So this one comes before similar triangles. And our result of similar triangles is based on this one. We will come visit this repeatedly in today's lecture. Okay, we will see. Okay, so with that generalization, let's introduce similar triangles and see how can we prove results about similar triangles. We have answered this in our homework. Let me draw a graph, then state the definition. A, B, C. Okay, for the two triangles, if all three angles are congruent, they have the same measure. And if the corresponding sides have the same ratio, then we see the two triangles are similar. And we use the symbol. We can see this is different from the congruent. Congruent, we have this tilde and equal. So here, the ratios are the same, but maybe not one. If this is one, then it's congruent. Not one, similar, not congruent. Okay, so we start with examples. The first example about similar triangles comes from the midpoint theorem. Okay, this is one of our homework questions. For example, I claim triangle and triangle AGF. They are similar. Okay, I will give a few minutes to think about it. Why? how do we check all these conditions? Are they all correct for this pair of triangles? Think about it. Kira, what do you think? How do you justify the
if you like prove that the sides are proportional and then the GF is parallel to BC.
Okay.
So basically if you prove like G and F are both like midpoints of the two of like
Okay.
AB and AC.
So very important. So this is E, F, G midpoints. Then by the midpoint theorem, we know that GF is parallel to BC. In particular, these two angles are congruent because they are the corresponding angles of two parallel lines. Then these two angles are congruent because they're corresponding angles for parallel lines. And we have a common angle. So now we have verified the first collection of conditions. Then the next one, we know this is the midpoint, ratio is 1/2. This is the midpoint, ratio is 1/2. And we proved this is half of BC. So the ratio is 1/2. So we checked AG over AB, AF over AC, GF over BC is 1/2. So therefore, the two triangles are similar. In the same way, you can prove G, B, E, A, B, C also similar. Okay, you can prove a few more of this. Okay. Then if we go to our second generalization, the 1/3, 2/3 points, we have similar triangles and the big theorem that we mentioned here. We can reformulate this theorem as similar triangles. Okay. Reformulate the big theorem. EF. The same condition, AE over AB, AF over AC. This implies triangles AEF So you can see our theorem give us plenty of examples of similar triangles. You give a triangle, you draw a parallel line to one side, then these two triangles are similar. Okay, let's see how to prove this. What do we need to check such that the two triangles are similar? We need to check a lot of properties. We need to check if the angles are the same. We need to check if the three pairs of sides have the same ratio. Okay, similar to what I had before. The two ratios are the same. So by the theorem, if this is R, the ratio is R. Now put them together. We see that the three pairs of sides, they have the same ratio. Okay, so this is the theorem. Okay. In this way, we verified the second condition. They have the same ratio. Now, the two lines are parallel. The corresponding angles are congruent. Corresponding angles are congruent, and they share a common angle. Therefore, the three pairs of angles are congruent. First pair, second pair, and a common angle. So we checked all the conditions needed for similar triangles. We checked all of them. Therefore, the two triangles are similar. Okay, so you see, this is a very difficult theorem. Without our big theorem, it's not easy to prove it. That if the two lines are parallel, the resulting triangles are similar. It's a very important one. Okay. Now we have some basic understanding of the similar triangles. We will recall and reprove the theorems. Okay. Given two triangles, we know the conditions are Okay. So let's compare the conditions here with the conditions for similar triangles. We can see we have the first part, but we are missing the second part. We have to prove that sides have the same ratio. How to check this? Okay. So when we define similar triangles, we have two sets of conditions. The first set we have assumed about angles. Second set about sides. How do we check that the sides have the same ratio? Okay, think about this. We will continue after the break. Be back at 8:18. Okay, 5 minutes break. Okay, guys, time to be back. Okay, now our condition. The angles have same measure. But we want the two triangles are similar. What's missing? The sides have the same ratio. Why? How do we check this? Okay. We will use these conditions one by one. First one, the two angles are the same. Two angles are the same. If the two sides have the same length, what happens? Okay, the first case, if AB and EF have the same length, what can you say about the two triangles? Even though they appear to be different, let's assume if they are the same, what happens?
They're both
Amy, what do you, okay,
I
who,
mean,
Aaron, yes,
both congruent.
they are congruent, yes, very nice. If they are the, okay, Aaron, what theorem do you apply?
SSS similarity.
Oh, but we only have one, it's not SSS.
Oops, I mean, yeah, right, that one.
So which one?
Let me check.
We have one side, two pairs of angles.
Right, that's ASA.
Right. Then we know that the two triangles are congruent. By ASA. So in particular, all sides have the same length. The ratio is 1. Similar. It's a special case. So this case is easy. In the following, we'll consider the complement case. What happens if they are different? We cannot apply the congruent theorems. What happens? In the following, we consider the remaining case. That the two sides have different lengths. Again, we break this into two sub-cases. AB is small, AB is bigger. Two possibilities. They have a different size. One is bigger, one small. And these two cases are exactly the same. So we only consider the second one. Only need to consider this one. Okay. Now we will see the two angles are the same. We will apply the superposition. We will make a move this over there so that this angle overlaps with this angle. because we assumed AB is longer. So if we move this over there, E will end up somewhere in the middle. It's a different color. Superposition. The same method we applied many times for congruent triangles. Okay, it's about the same. Then we draw a parallel line. We don't know what this point is yet. Let's call it H. Okay, so the steps, superimposition, impose E, F, G on ABC with angle E, angle A. Then draw F, H parallel BC. Now we have a parallel lines. We are in a position to apply our big theorem. Okay, let's think about it. What does the big theorem tell us when the two lines are parallel? Brett, Aaron, Peter, think about this. What can we conclude from this? If you have been taking notes, we'll go back to your notes and check the big theorem. What does it tell us? Kira, you have been taking notes.
Which one is the big theorem again?
Okay,
Like,
there's
which
only
step?
one big theorem. The one I boxed it. Okay, okay, now because we can go back, if the two lines are parallel, then the two sides have the same ratio. Okay, so then by our big theorem, then A E over AB, AH over AC, EH over BC. Okay, what does this tell us? Two lines are parallel, the corresponding angles, common angle, a common angle, corresponding angles, in particular, combined with this, we conclude these two triangles are similar. It's not what we want yet, but we are getting close. This implies AEH parallel to ABC. Not parallel, similar. lines are parallel, triangles are similar. Okay, a big step. With this, next we check these two triangles, AFH and EFG. I claim they are congruent. I think about why. So I claim what theorem do we have to conclude this? The two triangles are congruent. Again, we can apply the angle-side angle theorem. By our construction, we know these two angles are the same measure. These two angles same measure, which is the same as this one. And these two sides is a shift, so they have the same size. So angle-side angle theorem. We conclude the two triangles as congruent. ASA. Combine these two steps. We have that the two triangles are similar. Okay. So in the definition of similar triangles, we have two sets of conditions. Now we should that only the first set is sufficient. If we can verify they have the same angles, then the sides will have the same ratio. Okay, now I think we have we can modify our theorem slightly. We can find the points first, such that they have the same ratio. Then we prove the two sides are parallel. Okay, a different argument also works. Okay. A different argument. To find, I use E for F and H. Let me redraw this. Okay, a different proof. So you can see a tiny difference between this and the previous one. Both works. Okay.
Question.
Yes.
How come the F has a hat on top of it?
Okay. So here, because we previously, why there's no hat, that's a good observation. Because I make a copy of this over there. So I reuse the letter.
Ah,
I should have had. So here, that's why I use H. So we want to prove they are the same. This is not our assumption. This is our result. So here again, we want to prove the two triangles are congruent. This is a result, not an assumption.
ah,
So I use this to indicate they are related, but we will prove they are congruent. Okay, a little bit awkward. Sometimes if you drop this, should also be fine, but maybe a little bit better. Okay. Okay, so this is our first big theorem about similar triangles. We don't have to check the two sets of conditions. We only need one of them. And why? We prove it based on our big theorem. We make a congruent copy of the smaller one. Okay. Now we will go a little bit further. We don't have to check all three pairs of angles. We just need two. This is the AA similarity theorem. Two triangles. A, B, C, E, F, G. If we have two pairs of angles, then we say this is sufficient to conclude the two triangles are similar. Okay, think about this. Let's compare it with the previous one and see why. How could we just drop one condition? Aaron, why?
because you only need two angles to prove that the two triangles are congruent, because the third one doesn't exactly 100% matter.
Why? Does this imply
Hmm?
angle C equals angle G?
Let's see. Say yes. I mean, yes.
What's your argument? Why?
Right.
Okay, so this yes, because
since angle A always equals angle E, then and angle B already equals angle F, then you can assume angle G equals angle C because you already have two angles that are congruent.
Okay, so I think this is because of the interior angle theorem.
Right. Oh yeah, I forgot what that was called.
Angle theorem. The summation of the three is 180. Summation of the three is 180. Two of them are the same. The third one must be the same. So From the two, we get the third one for free. Then we can apply the previous theorem. The two triangles are similar. So this one is based on the previous theorem and the interior angle theorem. Combine the two, we have the AA similarity theorem. Okay, so 3 angles, now down to 2 angles. What if we only have one pair of angles? Another similarity theorem called SAS. We have maybe labeled angles, make it more easy to read. A, B, C. Okay, we go one step further. From 3 to 2, now to 1. We have only one pair of angles. Okay, now we need to compensate this. We don't have the second angle, but we have 2 pairs of sides with the same ratio. This again implies the 2 triangles are similar. Okay, let's see how to prove this. Very useful theorem, but why is it true? Okay, what theorem do we have that we can use to prove this? We cannot apply asimilarity because we don't know if these 2 angles are congruent or if these 2 angles are congruent. We only have one. Okay. It's not easy. So what we do is we will follow maybe a similar argument for this one. We will make a copy of the triangle. The 2 sides have the same ratio. So I will make a copy of this. Make a copy of this. Okay. Because the copy, I will label this F with a hat, tilde, G with a tilde. Okay, what do we have? We have a point F on AB. Okay, this can be done. We have G on AC. All right, now let's compare these two triangles. Okay. I claim AFG is congruent EFG. Okay, how do we verify this? What theorem could we apply for congruent triangles? Amy, any thoughts?
No. I
Try to use the condition here. Okay, so this two sides, yes.
wait, so could you like use like the big theorem thing?
Okay, so that big theorem will be for the second part.
Oh, okay.
So for the, we will keep it. So we start with an easy step. This easy step, these two triangles. What we know is same angle, same side, same side. What theorem could you apply?
SAS congruence.
Okay. Kira, is that what you thought?
No, I just is the AF equals EG supposed to be AF equals EF?
Oh, right. You are right. Yes.
Okay.
Yes. Let me correct myself. I write something incorrect. Okay, so now we have the, make this more compact. SAS for congruent triangles. Okay, now we have used the first condition over there. We will use the second condition combined with this. So I can replace EF with AF because they have the same length. I can replace EG with AG because they have the same length. So we have AB EF equals AC. I copy this one, then I do the replacement. This is AB over AF. This is AC over AG. So we have this identity. Okay. Because this is the condition we have, and this is our construction. Therefore, the two ratios are the same. Now we apply the big theorem. Two ratios are the same. This line must be parallel. The two triangles must be similar. Okay, the big theorem. The two lines are parallel. Two triangles are similar. Then we combine this with this. So this triangle is congruent to this one, which is similar to this one. So the two are also similar. So from there, we conclude Okay, not easy proof, but we have to use the same idea again and again and again, the superimposition. So this argument, superimposition, a very useful argument. Okay. And the big theorem, as we promised, we used it repeatedly. Whenever we have an equal ratio of the points, we have parallel lines, we have equal ratio. All right, one more theorem about similar triangles. The SSS similarity.
Excuse me?
Yes.
On the note sheet, you wrote something about trigonometric functions. When are you gonna do that?
Maybe next time.
All right.
Okay, so
Okay.
similarity theorem. Okay, let's get these two pairs of triangles. Oops. I can change this slide. Okay, that's not similar. Okay, let's track what we have done. We started with 3 angles. We get similar triangles. Use the interior angle theorem. We can reduce to two angles. We get similar triangles. If we have extra information about the size, we only need one pair of angles. So 3, 2, 1, and the next 0. We don't need any angles as long as we have more information about the size. Then the two triangles are similar. Okay, how do we prove this? Okay, so this is a very useful theorem, but why? Missing piece. Again, we will use the superimposition idea. We want to create a copy of this triangle over there that are congruent. Okay, where do we start? We will start with exactly the same thing we had before. We start with F, G, F, A, B with AF, also EF, G, AC with AG, EG. And we connect this. Okay. Now we are slightly different in a slightly different situation as we have been before. Before, the two angles are congruent, the two triangles are congruent. Now we don't have this angle condition. We only have the two sides. So we cannot conclude that they are congruent yet. We will use an extra condition over there. Okay. So the two ratios are the same. We will apply the big theorem. This implies, let me copy the first pair of conditions. A, B, just a copy, nothing changes. A, C, E, G. Then by our construction, this is A, B over AF. And this is, again, by our construction over AG. Now we see they have the same ratio. This and this, they have the same ratio. Okay, Amy, what does the big theorem tell us?
That they are similar.
Okay, so the two lines are parallel and they are similar.
Yeah.
Okay, so now we know what the big theorems are. We conclude, you see, it's very important. We use it repeatedly for all our results about similar triangles. I use the big theorem for short. F, G parallel to BC and the ratio of G. If I call this R over BC is also R. Now we have used the first pair, but we haven't used this. If this is R, this is also R equals okay, so let's okay. So I reverse the numerator denominator. Let me correct this. So I reverse the numerator and denominator this time. So it will be BC over FG equals R, which is BC over FG. So from there, we conclude the two denominators. Oh. Okay. This also implies the two triangles are similar. Big theorem, triangle AFG similar to ABC. Now we compare these two triangles. What do we have? These two sides, same length by construction. These two sides, same length by construction. And these two sides, we just proved they have the same length. Now, what can we say about these two triangles? Are they congruent? What theorem? Okay, Kira, what theorem?
Same thing as SS, but with congruency.
Okay, so this time we have side, side, side. So all three sides. So by the side, side, side theorem, we have A EFG, congruent EFG. Okay, now we can combine them. This one is similar, which is congruent. So these two tend to be similar. Okay, so now we have two sets of theorems. One set for congruent triangles. One set for similar triangles. Congruent, we have this ASA corresponding to AA. Similarity. SAS have this SAS similarity. We have SSS, SS similarity. And after class, I suggest you review the proofs of these three similarity theorems. You can see how we use the congruence theorem to prove the corresponding similarity theorem. So this is built on the congruence theorems combined with our big theorem. So if we add big theorem, we move from congruent to similar. Okay, we stop here. Let me stop recording.